Okay, I think we are back and we are live. The camera looks fine. Perfect. So I think we'll just kick off where we ended yesterday. So I'll just flip this back over and zoom in here a little bit. Okay. And then we'll also zoom in here. And then I think we'll get started with Anki. So it's very important that Anki is done. But as you see, I've not done my normal deck today. So do as I say, not as I do, I guess. And today we only have 2 new ones and 2 to review. And I guess sort of to refresh on like the nature of Anki is that you're reviewing those things that you forget most, if that makes sense. So if you review something and you understand it well, it's going to push out into the future. If you review something and you don't quite get it, it's going to bring it closer to the present. And so this means that you're interacting with those things most that you don't know well, and that if you really have something super down, you won't see it very often. And it's just really good for maintaining a good knowledge base and then also helping you discover holes in your knowledge. Because when you forget a particular topic or particular thing or what have you, you're going to not remember it. And so, you won't know that you've forgotten it. And so Anki or other learning software helps you to remember that you've forgotten it. So, yeah, let's just go in. Okay, so I know there are these 2 that I was unsure about for the power laws. So I think I want to probably, I think I'll wait, but I will be looking into the power laws more and starting doing some exercises. Or I guess I will be doing power law exercises when I get to them. So the root limit law, I wanted to say that actually, this is the unique one. So for most of them, you just apply the particular operation you're doing for the limits. So if I'm adding or subtracting, I add or subtract the limits. If I'm dividing or multiplying or dividing the limits. And even for power, I believe that you're also raising these limits to like to a power. So I think I'm going to watch a brief video on the root limit law. And then, let's see. Okay, it looks like we don't have a root limit law, so I'm just going to go. Oh, never mind. We do have a root limit law. I'm also going to look at root limit law. Oh. Okay. So the limit in a So could you give me an example of finding the limit in a calculus problem where you need to apply the root limit law? Okay, this looks like we're taking the root of the limit. This side of the equation. Okay, so if the limit of x to a, I'm going to zoom in, I can't see crap. If the limit of x to a, okay, that's visible on the screen as well. Maybe go even a little bit more. Let's see. Oop. Okay. The root limit law is a handy tool that tells us if limit x as x approaches a, f of x equals L, and n is a positive integer, then limit of x approaching a squared, or cut the n, square root f of x equals n square root L, provided L is greater than 0 when n is even, to keep things real. It's like taking the limit inside the root as long as everything behaves nicely. Okay. We're dealing with the square root here, which is the n equals 2 case of the root limit law. So let's break it down step by step. First, let's try to direct substitution. So we plug in x equals 4, and that evaluates. Make sure that it aligns with the root limit law and check if we need it or if there's more to consider. Could you rephrase this for someone who hasn't had much experience with calculus and is trying to understand the root limit law? Okay, yep, the root limit law is a shortcut that helps us deal with things like roots, square roots, or cube roots in these problems. If you got root in some expression, you can find the limit of what's inside the root and then take the root of the answer. Oh, okay. That's totally simple. Okay. So, as long as things don't get weird. Okay, so it looks like they are fairly plain. That, for like adding and subtracting, so pretty much we are evaluating the operators, or evaluating these expressions, and then that, or I guess it's to say we're allowed to evaluate our expressions when finding the root. Because this pretty much just said, which wasn't clear earlier on my Anki card, that like, as long as this is nice, meaning like not negative or some shenanigans, that I can literally just take the root of it. So, okay. I totally understand that now. Okay, so it looks like all of them are, so let's see. I wonder why. Maybe I want. Okay. That's actually fairly understandable. Okay. So limits can be understood in context of inputs and outputs, because for a limit, we're wondering what occurs as we approach. The input approaches a particular number, and then the input there, And then as that input approaches a particular number, what's occurring to the output for that? Power limit law means you can just like take the power of the limits of whatever expression you're evaluating or whatever thing you're evaluating. Yeah, so that's reasonable. Mathematical syntax for a limit. You have the little lim word and then x2 and then x with an arrow that leads to the number that is your limit, a in this case. Okay, perfect. So we've finished the cards and I accidentally closed Anki. Okay, so looks like we start back up here. Okay, let's see. What is the concept of removable discontinuity? Removable discontinuity. Discontinuity in calculus. Okay, so from what I understand so far, the discontinuity is when your function has a gap in the output, meaning like there's a particular input that is undefined on the output. And so a removable discontinuity, I would assume, would mean that when we have a discontinuity, it's removable if we can evaluate or we can algebraically change the expression such that it's still equal to the original expression, but no longer has that discontinuity. And the example of that one was where we had that expression that x plus 2 times x minus 2 over x minus 2. And so when that expression is all put together, if you have in 4, or if you put 2 in for x, then it's undefined because x minus 2 is 0, which would be in the denominator, right? Maybe I can show that. Doop. So if I had x minus 2 and x plus 2, and then I had x minus 2 here. If I tried to just have x equals 2, we would have a 0 down here, which would mean it's undefined, right? But I can cancel these out to where I just have this function, which is algebraically equivalent to the entire function before I cross them out, right? It's entirely equivalent to this function algebraically, but it doesn't have the undefined, doesn't have the discontinuity where x equals 2. Okay, I think that's reasonable. Let's see if we got it right. I think I was actually wrong there. And oh, lols. This is the exact this is the exact example. This must be a really common example for describing this. Filling it with a limit value. Okay. Okay, so I think that is it. Okay. That makes sense now. Okay, so for a given calculus problem, is it typically the case that we are given the limit, meaning we're given the input of the limit where x approaches whatever for the input, question mark? Okay, looks like in most calculus problems we're given the input limit, or this guy right here. Okay, and I'm looking for the limit's output. For any calculus problem that you'd find in Calculus 1 or 2, is it typically the case that you can use just the 7 or so limit laws and then boil down to what the value is as your limit approaches a particular input? Okay, perfect. So this was kind of leading the question, so this might be incorrect because I kind of told them the answer. So I don't want to super trust that, but I think I'm feeling all right about it. Yeah, because here I pretty much give them the answer, and yeah. Anyway, I know that finding limits will be important. Is the power rule for derivatives? Okay, so the power rule, so this is one thing. So I wrote this down, this power rule here. And now I'm trying to bring back or recall what this is. So I'm thinking the power rule, if we have a exponent in our function, when we're taking derivative, the slope of the tangent line can be found using the function that we get from the power rule. I don't know if that's the case. Oh, okay. Oh. Huh? That seems like it. Okay. Okay. That's crazy that you can find the slope so quick. Hmm. Um. Could you give me a definition or like maybe a partial proof for how this power rule works? It doesn't seem intuitive for me yet. Oh, okay. Derivative. I need to, yeah, I need to look into this function. Okay. Okay. Yes. So I will be looking into this later. I think it might be fun to kind of go through it all. Mm-hmm. Okay. So yeah, we'll look into that later. But for now, so we have the power rule. I think we will also do Oop. Oh. Oh, okay. They're not standard. All right. Okay. So I'm removing this input 1 because typically we're given the input of a limit. We understand removable discontinuity now. The square brackets thing. Oh, that makes sense. Yeah, it's the average slope. Well, yeah, okay. Like the average slope for those 2 points in the curve. I don't know about... Secant showing the average slope. I would like to know a little bit more about... I don't know. For me, it seems... Obviously, this is probably correct, right? But right now, it kind of feels hasty to have that be the average slope. Well... Yeah, I don't have an intuition for that yet, but... So what I'm saying here is so it talks about the secant here, connecting 2 points along the curve. This is in our video right here. And it's just, the grok is describing that this is the average slope between these 2 points. Yeah, and I don't have an intuition for that, but that seems reasonable. Okay, and then... I think that's a good answer there. And then I'm going to also do one is the concept of continuity in calculus. And what this is, I believe, is the idea that functions, because if we describe the discontinuity, the removable discontinuity, as a function where there is a discontinuity, meaning the output is, or the output of the input is undefined, or the result of the function is undefined for a given input. If that is the case, then continuity should be not that. Yep. Okay. When you describe breaks, jumps, or holes at a point, is this saying the same exact thing, or are you describing different things here? Oh, whoops. Oh. Interesting. Oh, so breaks, jumps, and holes are precise definitions, and each of these are something that make the function discontinuous. Okay. Oh, wait, there aren't super formal terms. Oh, rip. Okay. Okay. Oh. Okay, so an infinite discontinuity occurs when a function's limit approaches infinity at a point like 1 over 0 at x equals 0. Okay. A jump discontinuity. What do you mean here? What do you mean here in regards to left and right limits? What? What do you mean here in regards to left and right limits? Bruh. Left and right limits. Oh, I see. Okay. A jump discontinuity? Okay. Okay, perfect. So I now know that when we have discontinuities, there are like around 3 different types of discontinuity. It's probably the case that there are more, but these are probably the, the learner's, initial categories. Okay, perfect. I think we'll just continue here.
Now let's say that f of x is x cubed.
Let's see. Do I guys? Yeah, you guys can hear.
Using the power rule, the first derivative is 3x squared. So let's say if we wanted to calculate the slope of the tangent line when x is equal to 2. So the slope of the tangent line is going to be f prime of 2, which is 3 times 2 squared, so it's 12. So this means that at x equals 2, the slope is 12. So what does that mean? That means that as you travel 1 unit to the right, the curve will increase by a value of 12. So every time you travel, or every time the x value increases by 1, the y value will increase by 12. So that's what a slope of 12 means. Now let's draw a rough sketch of the original function x cubed. Now the graph doesn't have to be perfect, but just good enough for instructional purposes. And just to keep things simple, let's say at this point x is equal to 2. Now granted, the graph is not drawn to scale, so keep that. The y value will increase by 12. So that's what a slope of 12 means. Now let's draw a rough sketch of the original function x cubed. Now the graph doesn't have to be perfect, but just good enough for instructional purposes. And just keep things simple, let's say at this point x is equal to 2. Now granted, the graph is not drawn to scale, so keep that in mind. Now what we're going to do is we're going to estimate the slope of the tangent line using the slope of the secant line. Now to calculate the slope of the secant line, we need to choose 2 points. A point that's to the left of where you want to evaluate the slope of the tangent line, and one that's to the right. So this point is 2. We need to choose 2 points such that the midpoint of those 2 points is equal to 2. So we can use 1 and 3 for an example, we can use 1.9 and 2.1, or we can use 1.99 and 2.01. In each of those cases, 2 is the midpoint. But we're going to see what happens to the slope of the secant line as the 2 points, as we get closer and closer to the slope of the tangent line.
Okay, so as they get closer and closer to the slope of the tangent line, they will represent the slope of the tangent line. They're going to be yeah.
So first, let's calculate the slope on the interval from 1 to 3. So we use this formula y2 minus y1 over x2 minus x1. So y is the same as f of x. By the way, this is x1 and this is x2. So x2 is 3, x1 is 1. Y2 is going to be equal to the function when x is 3. Y1 is equal to the function when x is 1. So basically, to evaluate f of 3, we need to plug in 3 into that expression. So this is going to be 3 to the third power, and f of 1 is 1 to the third power. 3 to the third is 27, 1 cubed is 1, 3 minus 1 is 2. So we get 26 over 2, which is 13. So this is not a bad approximation for the slope of the tangent line. As you can see, 12 and 13, they're not too far apart. So I'm just going to write this down on bottom for reference. So now let's choose numbers that are closer to 2, like 1.9 and 2.1. So 2 is the midpoint. So it's going to be f of 2.1 minus f of 1.9 over 2.1 minus 1.9. So let's plug in 2.1 into that expression. So that's going to be 2.1 to the third power minus 1.9 to the third power. 2.1 minus 1.9, that's 0.2. So if you plug this in, you should get 12.01. And notice that this is a very good approximation to the slope of the tangent line. So notice that the slope of the secant line approximates the slope of the tangent line as these values get closer and closer to 2. Now, what was that something that helped us to evaluate a function as x gets closer and closer to some value? If you remember, it's limits. So we need to incorporate a limit expression with some sort of rate of change that looks like this. So let's use limits
Okay.
to evaluate the slope of the tangent line. So x is going to approach 2. And it's going to be f of x minus f of 2 over x minus 2. Now f of x, we know it's x cubed. F of 2, if you plug in
Let's see. So I understand up to this point where we're getting like closer and closer as the secant line, like the two values approach the tangent line. But then he whips out maybe this. Oh, wait a second. Okay. So, interesting. Okay. So he's using these, not the slope intercept, the, I guess, slope formula of y1 minus, or sorry, y2 minus y1 over x2 minus x1. And then he's using a limit to specify this particular point that we want the slope for. And then the powerful thing about this is that at a certain point, the tangent, like if we take the secant line, and those values approach, like he was describing here. As these values approach, this is like sort of a limit, right? Because we're getting like the instantaneous slope, which is the tangent here. So he's just plugging this in, and then we're doing calculus. Or I guess, yeah, I'd say this is calculus. So, interesting.
So that's going to be 2.1 to the third power minus 1.9 to the third power. 2.1 minus 1.9, that's 0.2.
Oh, we're at
So
2.
if you plug this in, you should get
We're at
12.01. And notice that this is a very good approximation to the slope of the tangent line. So notice that the slope of the secant line approximates the slope of the tangent line as these values get closer and closer to 2. Now, what was that something that helped us to evaluate a function as x gets closer and closer to some value? If you remember, it's limits. So we need to incorporate a limit expression with some sort of rate of change that looks like this. So let's use limits to evaluate the slope of the tangent line. So x is going to approach 2. And it's going to be f of x minus f of 2 over x minus 2.
Let's see. I don't understand. I thought it was the case that that it was the same here. But I don't think I... Oh, wait. Yeah, I'm not sure. I'm not entirely sure what... Like, why it is the case that we don't have the function expressions on the bottom as well. Let's see. Yeah, I'm not sure why that's the case. Oh, actually, we do the same thing up here. Let's see if he describes the reason why.
1.9 and 2.1. So 2 is the midpoint. So it's going to be f of 2.1 minus f of 1.9 over 2.1 minus 1.9. So let's plug in 2.1 into that expression. So that's going to be 2.1 to the third power minus 1.9 to the third power. 2.1 minus 1.9, that's 0.2.
Oh, okay. So, yeah. Okay, so I understand. Oh, okay. I think I got it now. Let me pull this up so this is clear. Okay, so what we're doing here is this we're on the top of the equation, we're evaluating the y's. And the bottom of the equation, we're evaluating the x's, right? And so an input for a function is x, and the output is y. And so in this given situation, I need to find my y's through using the function that we have. So that's why we have these functions up here, which evaluate. And then down below, then we have like just them regularly because that's what we want. Nice. Okay. Let's continue.
So if you plug this in, 2. And it's going to be f of x minus f of 2 over x minus 2.
Okay, so when we have the limit, looks like we are specifying the point as the second, or the limit as the second point, or I guess the second point here as the limit, and then we're looking as x approaches that.
Now f of x, we know it's x cubed. F of 2, if you plug in 2 into that expression, 2 to the third is 8, and you get this. Now we need to factor x cubed minus 8. So to factor differences of perfect cubes, you could use this formula. It's a minus b times a squared plus ab plus b squared. So to factor x cubed minus 8, x is a, b is the cube root of 8, which is 2, a squared is x squared, ab is 2x, b squared is 4. So this is how you can factor x cubed minus 8. So now we have this. The limit as x goes to 2 of x minus 2 times x squared plus 2x plus 4 over x minus 2. So now these two factors will cancel. And now we can substitute 2 of x. So we have the limit as x approaches 2 of x squared plus 2x plus 4. And so it becomes 2 squared plus 2 times 2 plus 4. 2 squared is 4, 2 times 2 is 4. And if you add 4 3 times, it's the same as taking 4 and multiplying it by 3, which gives you 12. And so we could use a limit process to find the slope of the tangent line, as well as just finding the derivative and plugging this in. So as you can see, the derivative is a function that gives us the slope of the tangent line at some x value. And there's multiple ways in which you can calculate the slope of the tangent line. You can estimate it using the slope of the secant line, or you can calculate it using that limit process. So I wanted to connect limits with derivatives in one video. Now the next area is integration, which is equivalent to anti-differentiation. As we said before, it's the process of finding the antiderivative. Now, if you recall, we said that the derivative of x to the fourth is 4x cubed using the power rule. Well, the integral of 4x cubed should give us x to the fourth. And here's the formula for finding the antiderivative, or the integral. So you're going to add 1 to n, and then divide by that result.
Okay. Okay. So since the integral process and the derivative process are inverse functions, then it would make sense that the power rule also applies. So I'm going to see what he calls that.
Of x to the fourth is 4x cubed using the power rule. Well, the integral of 4x cubed should give us x to the fourth. And here's the formula for finding the antiderivative, or the integral. So you're going to add 1 to n, and then divide by that result. And you're going to add some constant of integration. The derivative of any constant is 0. So when you integrate, you always have to add a constant to your expression. So this is going to be 4x to the 3 plus 1 divided by 3 plus 1. So that's 4x to the fourth over 4. And let's not forget to add plus c. And so as you can see, we get x to the fourth.
Okay, another thing is that we have plus c. So it looks like we just provide that. So when I was doing this earlier, or learning about this earlier, it wasn't clear whether or not the plus c was about like an actual constant, or it was a representation of the constant. But we're going through this problem, and it is merely like a representation of the constant. And so that's interesting to know. Okay.
Fourth plus some constant. So integration is the opposite process of differentiation. So you can call it anti-differentiation. Now I want to take a minute to compare derivatives and antiderivatives, or integration, side by side. Just so you can see a summary of the key differences between the two. So when dealing with derivatives, you're looking for a function that will tell you the slope of the tangent line, which touches the curve at one point, at some x value. So derivatives are useful for calculating the instantaneous rate of change. Now when dealing with integration, this will help you to determine how much something accumulates over a period of time, whereas derivatives will tell you how fast something changes per unit of time. So integration is very useful for calculating the area under the curve. So when dealing with derivatives, it will give you the slope of the tangent line, which you can calculate it by dividing y by x. To calculate the area, you need to multiply y by x. So notice the difference. So in the simplest form,
I like how this still comes back to the idea of slopes. Nice.
When you're differentiating, you're dividing the y values by the x values. Whereas when you're integrating, you're multiplying the y values by the x values. And multiplication and division, they're opposite processes. And that's essentially what you're doing when you're differentiating and integrating. Now, of course, it's a little bit more complicated than that, but that is the gist of it. Let's consider this problem. So
Okay. I think we'll stop there. I would like to capture this, but I think we will be there finished for the night. And we're at 17:18. Okay, perfect. What's incredible about this is that, like, as I'm going through, most of this stuff is already known. Oh, Daniel, you got the wrong guy. I'm currently learning, so you're actually ahead of me. Yeah, and so that's where we are at tonight. Yeah, hopefully Daniel finds some help, or can get some help. It would be a rip if he didn't get his homework done. Well, I'll see you guys tomorrow.